Hello everyone, I'm Xinlei from CISPA. Today, I'm going to share with you this work, Model Stealing Attack Against Inductive Graph Neural Network. This is a joint work with Yun, Yufei, and Zhang. Let's get started. Nowadays, machine learning has shown remarkable performance on various applications. For example, AlphaFold shows great ability in predicting the protein's architecture. And OpenAI published GPT-3 that can automatically write emails and business proposals, or even writing creative fiction. And a GitHub compiler can be used for code auto-generation. It can convert common to code and autofill for repetitive codes. In the real world, many data are graph, which has a combinatorial structure, have arbitrary size, and contains multimodal information. For example, social network, protein architecture, and knowledge graph. To better leverage the graph information, a new type of machine learning model called graph neural network have been proposed. To train a graph neural network, we first need a graph dataset that contains node feature and a connection between different nodes. The model can be trained for different tasks, such as node classification, link prediction, graph classification, etc. In this work, we focus on node classification task. We will introduce two settings of graph neural nets. In a transductive setting, the test graph is the same as the training graph, and the graph neural net is able to predict the class of unlabeled nodes. A more general setting is the inductive setting, where the model can generalize to other unseen graphs with same type of node features. In this paper, we focus on node classification tasks in the inductive setting. So a graph neural net can be represented as two parts, an encoder and a classifier. The prediction generated from the classifier can be used for node classification tasks, for example. Meanwhile, the middle layer embedding can be used for different downstream tasks, such as community detection. Also, the embedding can be further used to generate the Disney projection for visualization purpose. Graph neural nets have been applied by many big companies like Google, Meta, and Twitter. Once the model is trained, it can generate different type of response. For example, prediction, embedding, Disney projection, as we mentioned before. Despite being powerful, the data collection and the training process is also expensive, as it may take a lot of effort in collecting the graph data and tuning the hyperparameter of the model. After that, the trained model can be shared via cloud platform for commercial usage. For a benign user, he can leverage a query graph to query the API of the model and obtain the corresponding response to build downstream applications. In this paper, we consider an adversary whose goal is to steal the functionality of the GNN model. Concretely, the adversary queries the model with a query graph and obtain the corresponding output to train a surrogate model that has similar performance and behaviors as the target model. The adversary has two goals, step and reconnaissance. The goal of the step adversary is to build a surrogate model that matches the accuracy of the target model. The step adversary's motivation is compromising the intellectual property and violating the confidentiality of the target model. On the other hand, the reconnaissance adversary aims to build a surrogate model that closely matches the behavior of the target model. That is, The surrogate model seeks an agreement to the target model on any inputs. This enables the adversary to leverage it as a stepping stone to launch further attacks. For instance, the adversary can craft adversarial examples using the surrogate model instead of risking potentially detectable queries to the target model. Now let's talk about the attack taxonomy. We consider the adversary has the query access to the black box target model and can obtain the response such as prediction, embedding, and projection. And the adversary may also have a query graph, which has an adjacency matrix and all nodes features. In a more extreme case, the adjacency matrix is not accessible and the adversary needs to reconstruct the graph structure with the node feature first. We propose two types of attacks, where type 1 attack has the adjacency matrix and type 2 attack does not have it. And for each type of attack, the target model has 3 types of response, which in total result in 6 attacks. We then discuss our attack pipeline. Given a target model, the attacker first needs to reconstruct the graph structure of the query graph if they don't have it. Then the query graph can be used to query the target model and obtain the corresponding response, such as prediction, embedding, or projection. Then we use this query graph as well as response to train the first part of the surrogate model, leverage the label of nodes on the query graph to train the second part of the surrogate model to form a node classification model. In our experiment, we evaluate our attack using 3 popular GN models, that is Gene, GET, and SAGE. And we evaluate on 6 datasets. Regarding the configuration, we randomly select subgraph with 20% of node as the training graph, and we sample subgraph with 30% of nodes as the query graph. Later, we show that the query graph are still effective with much fewer nodes. And then we sample a subgraph with 50% of the node as the testing graph to evaluate the performance. Regarding the evaluation metric, we use accuracy and fidelity, where accuracy measures the performance on the original classification task, and fidelity measures the agreement between target and surrogate models. We first show the performance of the original classification task. We can observe that all GNN models achieve good performance on all datasets, which demonstrate that jointly considering node feature and graph structure are effective for classification. We then show the performance of type 1 attacks. As we can see from table 5, type 1 attack can build surrogate model close to the target model, given the response is prediction or the node embeddings. Take the PubMed dataset as an example. The target model achieved more than 0.9 accuracy score, while the surrogate model can consistently achieve at least like 87% accuracy score. These represent approximately 4% accuracy drop in all cases compared to the target model. We can also observe that type 1 attack can build surrogate model that offer usable accuracy even if the response is only a 2-dimensional Disney projection. We further conduct a study to show the similarity of the target and surrogate model. Concretely, we first randomly select a query graph to query both the target and surrogate model and obtain the embedding as the response. Then we projected them into 2-dimensional space using Disney. As we can see from this figure, for both target and surrogate model, they're able to separate nodes from different classes. which are denoted with different colors. We can see that different classes lie in different regions on the figure. Also, for the embedding with the same class generated from target and surrogate model, which are marked as triangle and cross respectively. Most of them lie in the same area, which shows that the node embedding generated from the target and surrogate model are close with each other. We then relaxed assumption of both target and surrogate models architecture and show the attack performance. We can observe that attack performance are very stable. For example, in figure 2C, when a target model is sage, the surrogate model can still achieve like 0.88 accuracy with Shen as its architecture, which further shows our attack is very robust against different model architecture. We then compare the performance of type 1 attack and type 2 attacks. Here, the type 2 attack means we need to reconstruct the graph structure first and then use the reconstruct graph to query the target model. So in this figure, the first row denotes the type 1 attack and the second row denotes the type 2 attacks. We find that type 1 and type 2 attack reach almost the same performance, and even in some cases, type 2 attack performs better. For instance, the surrogate model accuracy is 0.84 and 0.83 respectively in this case. So with suspect, the reason is that the row graph are not always optimal for the downstream tasks for different reasons. For example, the row graph may contain noisy or incomplete information due to the error-prone data collection, or their structure do not reflect the ideal graph topology after feature extraction and transformation. The query graph learned by the graph reconstruction framework in our type 2 attack are optimized toward the downstream tasks, for example, node classification, and this may achieve better performance in some cases. We then study the effect of graph reconstruction method to the final attack performance. We find that compared to random and KNN graph reconstruction, the IDGL reconstruction achieved better performance. This indicates that an effective graph reconstruction method does benefit the final attack performance. Later, we show how the size of the query graph affect attack performance. As we can see from figure 6, the attack performance are very stable, and our attack are still effective with only 3% of node in the dataset to form the query graph. This further shows the severe risk of model stealing attack against GNN, because the adversary can basically leverage much less data to launch an effective attack. We explore a straightforward defense that is adding Gaussian noise to the response of GNNs. As we can see from figure 7, the Gaussian noise only slightly affects the performance of the surrogate model. So which means more effective defense are still needed. In the future, we plan to investigate more effective defense based on differential privacy and watermarking technique. For a brief summary of our work, we performed the first model stealing attack against inductive graph neural nets, and we proposed a systematic design of threat model and different attack scenarios. And our attack can handle different types of response and achieve strong performance. Our code is available at this link. And this is all of my talk, and I'm happy to take your question.
Great, thank you very much, Xinlei, for your talk. We can see you and probably hear you. Yep, hear you as well. Anyone has questions? Yeah, please come to the mic, because this way it can be heard remotely as well.
Hi, interesting talk. So how many queries do you need in order to build a reasonably accurate surrogate model?
Yes, thanks for the question. So actually in our experiment, we see that maybe we can only use like only 3% of node in the data set that we are able to build a usable surrogate model that achieves similar accuracy or fidelity as the target model.
I'm not sure if you heard the question was.
So my question about the number of queries that you need to make to the original model in order to build the surrogate model. It's not the size of the query. The number of times that you need to query the model.
Actually, the number of times is proportional to the total number of nodes, because for each node, you only need to query the target model once, right? So after you get the prediction, that you can leverage this graph as well as the prediction to train your surrogate model.
So 3% you mean of the nodes?
Mm-hmm. Like you only need 3% of query to train. Let's say when you train your target model, you need 100% of query, but when you train your, let's say, surrogate model, you only need 3% of query.
Okay.
Yep.
Thank you. Any other questions? Okay, I actually had a question because you mentioned differential privacy as a way to defend against this attack. I was just wondering why you think it would be effective, and yeah.
Yeah, it's a good question. So actually, when we're talking about differential privacy, it may be able to hide some, let's say we can use differential privacy to hide some age information, so that maybe, as we also see in the paper, that the graph reconstruction method is very essential or very important to get a good attack performance. Like you need to reconstruct the graph perfectly, or nearly perfectly to get a well-performed surrogate model. But if you leverage differential privacy, let's say when you train a target model, they may, forbid you to predict the age connection between different nodes, so that the reconstruct graph may have lower quality, and that makes your attack less effective. Yeah.
Oh, I see. So yeah, so you would use differential privacy on the actual model protection as opposed to training data, because there is an intersection between.
Mm-hmm. Yeah, but it may also, let's say, decrease the target model's utility. As, for example, if you reduce the total number of age, let's say the original target model may take less information from its neighbor and give a less concrete prediction or less correctly prediction. Yeah.
Yeah. Thank you for clarifying, Xinlei. Any other questions for Xinlei? Okay. Thank you very much, Xinlei, for joining us.